Hi, this is Jagdish, Assistant Professor of EC Department, SNS College of Technology, Coimbatore. And today, in our video lecture topic, we are going to discuss about the SiC DMOSFET. Let's get into the topic. So, SiC DMOSFET, what is that? Silicon Carbide MOSFET offering significant performance advantages over silicon superjunction MOSFET. The silicon MOSFET delivers an outstanding improvement in high frequency switching power converter applications. So, these are all the planar SA MOSFET and planar SiC MOSFET structure is given in this diagram. Then SiC devices do not need conductivity modulation to achieve low on resistance since they have much lower drift layer resistance than SiC devices. MOSFETs generate no trail current in principle. SiC deliver much higher electron saturation velocity and much lower capacitance, providing substantial benefits in higher speed switching and decreased power loss. And this is the SiC MOSFET module, and here it is a SiC MOSFET symbol. It looks like the simple JFET. There is a junction field effect transistor like gate drain source. And the device structure and characteristics. SiC MOSFETs have much lower switching loss than IGBTs, which enables higher switching frequency, smaller and less expensive cooling system. Compared to 600 voltage to 700 voltage silicon MOSFET, SiC MOSFET have smaller chip area mountable on the compact package and an ultra low recovery loss of body diodes. For these reasons, SiC MOSFET are increasingly being used in power supplies for industrial equipment and inverters converters for high frequency power conditioners. And here there is a graphical representation which is given for blocking voltage to area specific resistance is given here. Here the SiC DMOSFET, SiC superjunction and SA MOSFET, the characteristics given over here. And the VD and ID characteristics. Since SiC MOSFET have no threshold voltage, that is a penny voltage, as IGBT, they have low conduction loss over wide current range. So SiC MOSFET on resistance at 150 degrees Celsius is more than twice the room temperature, whereas SiC MOSFET on resistance increase only at a relatively low rate. This facilitates thermal design for SiC MOSFET and provides low on resistance and high temperatures. And here that is a VD and ID characteristics is given over here for different temperatures. The first characteristic shows Ta equal to 25 degrees Celsius and the second characteristic shows Ta equal to 150 degree Celsius. So the graph is plotted for drain to source voltage, that is VDS, and drain current, that is ID. Turn on characteristics. The double pulse clamped inductive load test setup below is used to compare switching performance of two half bridge circuits. On one half bridge uses ROM's SCH2080KE SiC MOSFET co-packaged with SiC SPD. Then the other uses SI IGBT co-packaged with SI FRD. So 10 on characteristics circuit diagram is given over here. Here we have 400 voltage supply and 200 microfarad capacitance, and DUT doubled test pulse is there, and everything is connected. It is for a turn on characteristics. The turn on switching rate of SiC MOSFET is several tens of nanoseconds, which is equal to that of IGBT and SA MOSFET. However, inductive load switching causes a recovery current from commutation to the upper arm diodes to pass through the lower arm. SiC MOSFET body diode has recovery performance equivalent to that of discrete SiC SPD, but it has higher VF. The fast recovery performance of diode reduces turn on and loss by several tens of percentages. Turn off characteristics. The most distinguished feature of SiC MOSFET is that they do not exhibit tail current as observed in the IGBT. Therefore, SiC MOSFET can turn off loss, that is E of, that is approximately 90% smaller. And turn off characteristics is given in this graphical representation. So turn off characteristics, IGBT's high switching loss increases the chip's junction temperature, frequently limiting the switching frequency to 20 kHz or less. The much lower E of allows SiC MOSFET to switching at much higher frequency, 50 kHz and higher. The size of passive and or cooling system, this can be significantly reduced. So forward characteristics of body diode, like SiC MOSFET contains a parasitic. The parasitic means that the body diode formed in PN junction. However, SiC MOSFET body diode has high threshold voltage around 3 voltage and relatively larger forward voltage drop due to the fact that the band of SiC is 3 times larger than that of Si. So forward characteristics of body diode is given in this diagram. So forward characteristics of body diode, when connecting an external anti-parallel freewheeling diode to the SA MOSFET, an additional low voltage blocking diode needed to be connected to the MOSFET in series to prevent the conduction through the slow body diode. This because VF of SA MOSFET body diode is about the same as that of the external diode. This means more components and higher conduction loss. Such arrangement is not needed with SiC MOSFET since the VF of their body diode is sufficiently high compared to that of a typically external freewheeling diode. This is the reverse conduction characteristics. So reverse conduction, the high VF of the body diode can be reduced by turning on the gate voltage for reverse conducting like synchronous rectification, since it in inverter drive that the gate of switching devices is often turned on in the arm of the on commutation side upon the completion of dead time. Commutation current is applied to the body diode only during dead time. So this is a schematic cross section of unit cell of SiC DMOSFET. The lowest possible conduction losses can be achieved with the SiC MOSFET, that is given over here. So concept for use of SiC as a wafer material for vertical DMOSFET. So it can achieve high VDSS in the narrow depletion layer and can increase impurity concentration, allows for drastic reduction of drift layer resistance. Thank you.